A possible solution for such equations is an exponential. Because if we set x, in fact x of t, as let's say e to the rt, it's an exponential for the time. So where r is a let's say constant. Okay. Let us see x and its derivatives. If x is chosen to be e to the rt, okay, and r is a constant, then what about x dot? It is r times e to the rt. Of course, this exponent will give a contribution of r. And x double dot, there is one more r and another r coming, so r squared e to the rt. Therefore, the equation will be, this equation will be now x double dot, what is it? R squared e to the rt plus 2 beta x dot r e to the rt. And next, omega 0 squared e to the rt equals 0. So again, you can cancel through the exponentials. That's why we have chosen exponential as the possible solution. So e to the rt's will disappear. What do we have now? We have an r squared plus 2 beta times r plus omega 0 squared is equal to 0. And we remember this kind of equation. It is like a quadratic equation. It is like, for instance, ax squared plus bx plus c equals 0 form. And we know how to solve such quadratic equations, to how to find the roots. Remember the formula, R1, 2. The possible roots that satisfy this equation is, of course, A here is the coefficient 1, B is the coefficient 2 beta. Of course, this B is not the other B, just by coincidence, because the A, B, C are the coefficients, but this B has nothing to do with those coefficients. It is just the proportionality between the velocity and the resistive force. And this C is omega 0 squared. And we remember this formula from previous courses. It was minus B plus or minus B squared minus 4AC divided by 2A. So let's just substitute A, B, and C. So R1 and 2 minus B, but B is 2B. 2 beta minus 2 beta plus or minus root 2 beta squared minus 4 times AC. A is 1, C is omega 0 squared, all divided by 2b, which is just a 2. If you simplify, this becomes 4 beta squared. This is also a 4. A 4 will come out as 2. So there is a 2 here, 2 here, these 2's will cancel. So R1 and R2, these are the possible roots in this calculation. Minus beta plus 2's cancel, beta squared minus omega 0 squared, and this is minus beta minus. So the only difference is the sign of the second term. Is it plus or minus? So both can be correct and will be taken into account. Minus beta minus the root beta squared minus omega 0 squared. So that if these are the solutions, these are the roots, and the solutions are the following. For instance, x of t will be an unknown magnitude will be assigned. So we have e to the minus beta t and a1 e to the rest beta squared minus omega 0 squared times t plus another amplitude a2 e to the negative of that beta squared minus omega 0 squared and t. But now that we have three possibilities, we have three possibilities depending on the relative magnitudes of beta and omega 0. Case 1, because depending on these possibilities, the type of function, the type of solution will be obtained. First case, let's look at the root. Here we have one possibility, omega 0 squared is greater than beta squared. Omega 0 squared is greater than beta squared. Second possibility, they are equal. And third possibility, the other is greater, so beta squared is greater, therefore omega 0 squared may be less than beta squared. And it depends strongly, the motion depends strongly on this comparison. So in the first case we have imaginary roots because omega 0 squared is greater than beta, therefore we have imaginary roots, and the type of solution is, a type of motion is underdamped. Underdamped. Second case is critically damped. And the third one is overdamped. Okay. Now there are three possibilities, as we said, depending on the relative magnitudes of the omega 0 squared and beta squared. Because in the square root we have three possibilities. Maybe omega 0 squared is greater, maybe the other beta squared is greater, or maybe they are equal. Let me plot all of them on the same graph first. So along the horizontal axis we have the time, and the vertical one is the position. For the first one we have underdamped case. Underdamped is the only oscillatory one, because the others are not oscillations. Underdamped case can be represented by this function, for instance. On the one hand, it is making oscillations, on the other hand, the amplitude is getting less and less. The second possibility is critically damped case. And the third one is overdamped. So the first one is number 1, underdamped. The medium is number 2, critically damped, and the third one is third, which is the overdamped case. The second and third are not oscillations. First one is made of oscillation, but it is not periodic, because in the first one, let me just consider first one as a whole, number 1 in more detail. In this case we have the root of, what was the root? Beta squared minus omega 0 squared. Let me write the full root. So R was minus beta plus or minus beta squared minus omega 0 squared. But we say that the second one is larger, so that inside we have, inside the root we have something negative. So we understand it is, we will have imaginary functions, I. So that the solution is x of t, for the first choice, will be e to the minus rt, e to the minus beta t, multiplied by an amplitude, unknown amplitude, a1, e to the I omega 1t plus another amplitude, e to the minus I omega 1t. What is omega 1? Omega 1 is a positive number, positive frequency, where this omega 1 is defined as omega 0 minus beta, so that let me make it a definition. So omega 1 is a positive number because we changed the order. And these are imaginary functions. But we can also write this function in a new way, in a sinusoidal way. X of t will be an amplitude A e to the minus beta t cosine omega 1 t minus a certain delta, for instance. So this is the function that describes this motion. Now let's draw the first one as a single case. We are still considering number 1 under damped motion, x. Now this is the sort of function. And we have a certain beta. For instance, this is the envelope. This is the envelope. Therefore, this part corresponds to the e to the minus beta t. Sinusoidal part corresponds to omega 1 t minus delta. So if we multiply them here with a certain amplitude, that amplitude corresponds to the value of x at the beginning. Because at the beginning, for instance, if you neglect the delta, face the factor delta, then a is the amplitude at the beginning. So this drop of the amplitude is because of the negative exponential, and the sinusoidal behavior is represented by this cosine function. But if there were no beta, for instance, it would be a normal sinusoid. And this is the case without any attenuation. Here it is no damping. No damping, undamped is beta is 0. If there is no beta, there is no slowing term, there is no resistive force. It would be just a sinusoidal motion without any attenuation, any drop in the amplitude. X of t would be a normal sinusoid or a cosine or a sine, they are the same. But if we have a beta, then these amplitudes should be less and less in time. For a greater beta, it will reach 0 in a shorter time interval. Now what about the second case? Let's first see the three types in more detail and then solve some examples. Our second case was the critically damped motion. Second is this was under damped, this is the critically damped. Critically damped motion is the following. First of all, what is the solution? Or what are the solutions for this critically damped case? Remember that in this case, omega 0 squared is beta squared. So what happens to the root? We have repeated roots. Because remember, R1 was e to the minus, R1 was minus beta plus beta squared minus omega 0 squared. And R2 is the same minus beta but minus beta squared minus omega 0 squared. However, we have now a 0 in the root. So this is 0, this is also 0. Then R1 and R2 are equal. Equal roots or repeated roots. Equal or repeated roots. But what is the function x of t in this case? Of course, we first have, we necessarily have e to the minus beta. What comes next? We don't have imaginary roots, we don't have real root, we have just the same root but repeated. But we should have a second solution. since it's a second order differential equation, second order linear constant coefficient, but the important thing is it's a second order case. For a second order differential equation, we should have two solutions, two independent solutions. One is alright, but what about the next? Since it's a second order differential equation, we should have a second solution. What was the first? The first one is, let's say, x1 of t is an amplitude, for instance, an amplitude a, e to the minus beta t. What about x2 of t? It is similar to this, but with a difference. Let me mathematically show what we should have. Maybe you remember from differential equations courses the second solution to this kind of case, but let me try to show it briefly. Because we have the equation b minus r squared applied on x is 0.